Welcome back, everybody, to the second part. So where are we? Yes, we are trying to squeeze large lists of sorted integers into as little space as possible, into as few bits as possible. And so far, what we have is a combination of two tricks. The first trick is that we encode the gaps between the numbers and not the numbers themselves. And that we can do because it's a sorted list. So there's no negative numbers. And the second thing is that we found a way to make it elastic. The fact that small numbers will have few bits and larger numbers will have many bits, and it grows as much as you want. There is no limit to the integers we can encode. All right, and plus it's a prefix code, which has the very nice property that if you just feed the memories with these encodings, you don't even need any pointers or anything to tell you where it starts and where it ends, because you can just figure it out just scanning through the bits from the left to the right. Okay. I'm repeating myself, but no free lunch. This encoding is going to cost a bit of CPU, so you have to, the CPU needs to work a little bit. But the benefit is that it takes less space in the on disk and in the memory, right? And so it's always a compromise to find. You know, sometimes if you notice typically that you know, whenever I'm going to try to explain it without actually starting an hour lecture on that, but whenever something is slow in a system that you build, usually, or even almost always, it's either the CPU, or the memory, or the disk, or the network. It's one of these four. And so the way you make things faster depends on who is to blame for being slow. And very often in this kind of situations, it's the disk that is at fault. And when it's the disk that is too slow because you're trying to read and you have a maximum number of bits per second you're reading, and the CPU is idle, this is when you want to compress. Because the CPU is idle anyway. So if you ask it to start decompressing data, then that's fine because it had nothing to do anyway. And then, because you reduce the number of bits that you need to store the data, then you solve the problem that the disk was slowing you down because now you have less bits to read per second, right? Who is with me? Right? So it's a great fit right here, right? We squeezed so that makes it easier and quicker to read from disk. It takes more time, but this is fine because the CPU didn't have anything to do anyway. So it's a great fit. All right. Now I told you it's a parameterized encoding, meaning that you have a choice on the size of the packets. And of course, having too much choice can be not so good, right? And that's what marketing people know. If you have too many products and too many colors and too many sizes, then the customers are lost. But if you only provide them with few choices, then you increase the sales of the product, right? So here, that's kind of the problem of a parameterized encoding like that, is that you need to specify a parameter. So now the compromise is like this. You have either big packets, but in that case, it doesn't compress that much, right? Because you anyway store on many bits, but it has the advantage of little overhead for the CPU. On the other hand, if you have very small packets, let's say 4, 2 would also work, but I told you 2 is ridiculous, right? But let's say 4 packets, 4-bit packets, then it's very compressed because the very small integers are going to be super small in the size in bits, but it's putting more efforts on the CPU to decode all of that. Where do you put the slider on this to pick the size? I would say 2 factors to consider. The first factor is this balance between the CPU and the disk, right? Basically, what's going to happen is that if you don't compress enough, so that would be on the left side, then it takes forever to read from disk and the CPU has nothing to do. But if you go too extreme and go to the other side that you compress so much that now the CPU is basically too slow and the disk is idle, then you went too much to that size. So you need to find the sweet spot in the middle where the CPU and the disk are mostly balanced. And then you found the sweet spot and the right parameter. So this is, it's basically a bit of trial and error, right? And the other factor to consider has to do with information theory and entropy, and that depends on the distribution of your integers. But that I'm leaving for later, right, to show you that. Because if you are in a system that has a lot of very small integers, then you probably want to go for a lot of compression, right? Because most of your integers are going to be very small, so you're saving space. But if you are in a system that has a lot of very large integers, then maybe you would be more on the left, right? So it really depends. This is the short answer. It depends on the distribution of the integers, and it depends on this balance between the CPU being idle and the disk being idle. Right? Who is with me? Right? So it's nice because there's a lot of very generic principles of computer science in there, right? Even though it's a very specific thing right here. Okay. But can we do even better than that? Because I told you the going to small packets of just 2 bits is ridiculous. Well, it's ridiculous if you use the variable byte encoding, but it turns out we have something that does go bitwise, and that is incredibly powerful. And as we will see, it's even optimal from an information theoretical perspective. It's like the holy grail of the encodings in terms of integers. But I will show that to you. It's known as the gamma encoding. Who has ever heard of the gamma encoding? Who has never heard of it? Oh, you're going to love it. This is absolutely fantastic. But before I show you the gamma encoding, I would like to show you the Unary encoding. It's also called the thermometer encoding for a reason that you will very soon understand. The Unary code basically encodes a number by writing just as many ones followed by a 0. So you want to encode 12, that's fine. You encode 1, 1, 1, 1, 1, 12 times, and then a 0. Who would be able to encode that for every integer I give you? It's very easy, right? Who thinks it's a waste of space? Right? It looks like it's a waste of space. We'll actually see that encoding is actually optimal for some distributions, very surprisingly. But anyway, yes, that's the Unary code. That's the thermometer encoding, where we just encode like this. Who agrees that it's a prefix code? If I give you plenty of numbers and sequences of bits, you would be able to decrypt, right? You just look for the zeros. That's basically how you tell. All right, so that's the temperature encoding. Unary code is the formal way. Thermometer is just the nickname that people give to it because that's basically a thermometer, right? It's like reading the temperature. Okay, so that's how it looks like in the encoding. But of course, that's not it. We are not, don't worry, we are not going to encode the postings list with this, but this will be an ingredient of the gamma encoding, this Unary code. So you told me you're able to decrypt that. Are you? So who is able to decrypt that? If I tell you that's a temperature encoding, who would be able to tell me the integers? Right? You just locate the zeros, and that's it, right? That's easy. So again, what I like about the thermometer encoding is that it's a prefix code. That's very important. It's a prefix code. Okay. I was thinking a world in which these would be the phone numbers, but that would take a while to actually call people, right? Okay. So the author of the gamma encoding is Peter Elias, that you see right here from MIT. And he had this brilliant idea on how to apply this thermometer encoding to encode any integer in a bitwise fashion, highly compressed and optimally compressed even, up to a constant factor, but I'll come back to that. So here's how we encode 19. So probably you guess the first thing that you do, it's this irresistible urge is to turn it into base 2, right? You want to encode it to bits, right? That's what every computer scientist immediately wants to do. So let's do that. 19 would be 10011, right? In base 2. Now, who agrees that in base 2, any integer except 0, so higher than 0, starting with 1. What is the first bit of the base 2 encoding of any integer? One, it's going to be 1, right? Sadly, it doesn't work in base 10. If I tell you what is the first digit of any integer, then you don't know because there's 9 possibilities, right? But what's really cool about base 2 is that if you don't waste any zeros at first, you know for sure the first bit that comes is anyway going to be a 1. Why is that interesting? It's because we don't need to actually encode it because we know it's a 1 anyway. So the first trick of the gamma encoding is to have special treatment for the initial bit that is always a 1 in any case, right? It's always a 1. So we just remove it and we can add it back when we decode, right? So now I want to encode this sequence of bits 0, 0, 1, 1. That could actually be any sequence of bits for any integer I want, right? So it's just an arbitrary sequence of zeros and ones. So I'm going to take that sequence of zeros and ones just without the leading bit. That's the only thing that I'm removing is the leading bits. That's always a 1. That here is 1/2 of my gamma encoding. I'm already done with 1/2. That's the right half, right? So I put all of the bits except the leading bit. Now, it's elastic, right? So I need a way to make it a prefix code. So I need a way for somebody to know that these are going to be 4 bits to decode. How do we do that? You might have guessed temperature encoding, thermometer encoding. So this size 4, we encode as 1111, right? As many ones as there are bits on the right, followed by a 0. That is the thermometer encoding of that length, right? And that gives me the gamma code. That's it. Would be able to do it for any integer greater than 0, right? Yeah. Awesome. So that's it. That's the gamma encoding. What comments can I make here? Well, who sees that the bit that is in the middle is always going to be a 0? You see that, right? Who sees that the gamma encoding is always going to have an odd number of bits? You see that too, right? It's never going to be even, always odd. Okay. And in fact, it's always going to be plenty of ones on the left side, then a 0, and then the bits of the integer without the leading one. That's it. That's the gamma encoding. Now, also as a very rough rule of thumb, who agrees that very, very roughly, the size of that encoding is going to be double the size of the base 2 representation? Very roughly, right? Very roughly. We just double. And in fact, the way you see it is just that you technically take the base 2 representation and then you just mirror it with plenty of ones. That's what it does. So just to give you the impression of the gamma encoding, right? Okay. Now, let's do it on the list of all of the smaller integers. So let's encode 0, 1, 2, 3. So in binary form, that's 0, 1, 1, 0, 1, 1, right? The binary form without the leading one is going to be for 2 and 3, that's going to be 0 and 1, right? And now you already start noticing we have a problem with 0, right? 0 and 1, they kind of collide. So in fact, that's the reason why 0, in fact, is not included in the gamma encoding. You just do not encode 0, right? So we are just going to encode 1. The length of the former sequence, so that's basically the number of bits minus 1 of the total representation. In Unary, so that would be the Unary encoding of the length. Right, so they have a length of 1, so that is 1 times 1 once 1, right? And then the gamma code. So again, I told you 0 doesn't exist, we just don't encode it. 1 is just encoded with a 0, right? It's still an odd size, and it still has a 0 in the middle, which is the only bit that it has, right? So it still fulfills the property I told you, right? But 1 is just a 0. Then you have 2 and 3. It's incredible because 3 bits, 2 and 3 fits on 3 bits. Just that, super efficient. Then you have the next, so 4, 5, 6, 7. These are the binary representations, and you see they have 3 bits. So I remove the leading one. You see it's always a 1, the first one, so I remove it. How many bits are there? 2. And the temperature encoding of that, 110, and that gives me the gamma code. Now, and 5 bits for these 4. Then I have the next 8, which are going to be 4 bits, 3 without the leading one. Temperature encoding, that's now 7 bits for the gamma code, and so on, and so on, and so on. You see how it's elastic. It just elastically grows with the integer. Now, also to give you a very, to make you think about it, who agrees that this here is basically the log in base 2, the logarithm in base 2, rounded or approximated to an integer, right? You know that what the logarithm gives you is the size of the decimal representation for the logarithm in base 10, the size of the binary representation if you take the logarithm in base 2, right? So this is very roughly the logarithm. Okay. Very good. So these are the gamma encodings of the first integers. Now, what do you do if you want to encode 0? You just offset by 1, right? You can make a convention that you just encode the integer plus 1, and then you can encode 0. So that's easy, basically. It's not a problem at all that we cannot encode 0, because in practice, you just offset. All right, so that's very good. Now, what are some of its properties? You agree it's a variable length encoding, right? Elastic. Small integers, very few bits. Large integers, lots of bits. You agree it's a prefix encoding, right? That I haven't shown yet, but who agrees that it's a prefix encoding? You see why? You look at all the ones that you have until you reach a 0, and then you know how many ones there are, and then you know how many bits you need to read after the 0. So it's a prefix encoding. All right. Universal encoding, that's new. That I haven't actually discussed before, universal encoding. Universal encoding basically means that it is optimal whatever the distribution of your integers is. That's a universal encoding. It's basically optimal up to a constant factor. But that I'm going to make more precise by going into a little bit of math regarding the universal encoding. Who is scared of math? Who loves math? Wow, theoretical computer science has a lot of math, right? Who is taking the information theory lecture? Who will take the information theory lecture? So, yeah. Okay, so I have to tell you, I'm not an information theorist, right? So I don't know as much as the lectures of information theory, but I know a little bit, and just enough to explain what I'm going to explain here. Okay, so I'm going to explain what I mean with the gamma encoding is optimal. So the idea behind entropy, who heard of Shannon entropy? Who never heard of entropy or Shannon entropy? Don't be shy, you can raise your hand. It's okay to not know, right? Okay, so I'm going to explain that. So here's the idea. You have to imagine an experiment with 2 people, Alice and Bob. And Alice has to communicate a number to Bob. In order to communicate that number to Bob, she needs to send zeros and ones over some channel, right? And that's the only channel. They cannot speak, they don't have any other communication, right? They have to send it over a channel. And so the idea is that there is the integers that Alice has to send, she receives them by some sort of random generator that just gives her some numbers according to a specific distribution. That distribution is given by a random variable. Who heard of random variables? Right, awesome. We're going to have random variables in a few weeks with probabilistic information retrieval, so be ready for that. So anyway, I have this probability distribution on integers, and Alice is given that number, and she's supposed to send it to Bob. And so, of course, they can encode it in a certain way. They can choose the way in advance how they are going to encode it. And so, of course, you want to do it optimally, right? You would like to find some strategy or find a way to encode everything in such a way that it's the smallest average number of bits that you can possibly achieve on average, right, based on the probability distribution. What's important is that it's compressed, but it's lossless. Lossless means that Bob can retrieve the original integer. There is no loss, no information is lost, right? It's not always the case. There are also compression schemes that might lose information. For example, when you encode movies or series or pictures, JPEG, for example, is not lossless, right? You lose a bit of information, and the benefit that you get is that it's a very small size. But here it's lossless. You want Bob to be able to decipher the integer. Okay. So they have to decide on how they are going to encode these bits over the channel. Now, Shannon is the name of the person who actually managed to find an answer to that question and who is able to give you the answer that this is the smallest average number of bits that you are going to need, and that is the Shannon entropy. Now I'm going to tell you how it's done. It's basically done by looking at some function that is called the amount of information, letter I. I'm directly giving you the formula. It's actually minus log p, where p is the probability of seeing a specific number. So now I'm going to just take some time to be clear on the notation, and that's something that I will even repeat in a couple of weeks. What does everything mean in here? X, here, the uppercase version, that is my random variable, the one I have here. That's my source of integers. That random variable is basically, very roughly speaking, it has a probability distribution over the integers, right? That's px is basically the probability distribution over the integers. And px basically gives me, for every number that I squeeze in there, it gives me its probability, right? It could tell me, for example, there's a probability of 1/4 that the number is going to be 0. There's a probability of 1/2 that it's going to be 1. There's a probability of 1/4 that it's going to be 2, right? Then we say that px of 0 is 1/4, px of 1 is 1/2, and px of 2 is 1/4, right? So far, so good. So this is px, that's the probability distribution that is associated with the random variable uppercase x. Small x is not a random variable. Small x is just a 0815 mathematical variable, the way you see that every day, right? It's just replacement for some integer, small x. So having seen that, you can see now what I have on my screen right here is basically a function of the integer that I'm sending over the channel, this small x, that gives me the amount of information. But it has a dependency because that depends on what I have in here. That depends on what distribution I have in here. So this is why we have this subscript here that gives me the random variable based on which you compute that amount of information. Right. Now, there's a simpler way in the way that I think about the information. I think of it as surprise, the amount of surprise. Because imagine that you have a distribution that is deterministic. You have basically this source here of integers always spits out 42 after 1 million years, right? But it always gives you 42, no matter what, probability of 1. So px of 42 is 1, and px of anything else is 0, right? Now, you push the button of this source, and what comes out is 42. Who is surprised? Nobody is surprised, right? It's a probability of 1 that it was going to be 42, right? So now if I come to you and I tell you, oh, by the way, it spit out 42, you're going to be like, yes, so, and what? You know, I'm not surprised at all. That's already deterministic anyway. I knew that. How much information is there in here? 0. You didn't learn anything. That's something you already knew. Who sees that? Right? And this is why you see this magical formula that I have here. If the probability is 1, what is the log of 1? It's 0, right? I'm here. So it basically means that if there is an integer that, according to my distribution x, if there is an integer that has a probability very close to 1 of being spit out by the source of integers, then I'm not surprised at all. Now, imagine that I slightly modify the source. Now it spits out 42 with a probability of 99.9999999%, and maybe it spits something else with an extremely small probability. Now I come to you and I tell you, okay, I push the button of this machine and it spit out 43. Now you're going to open your eyes. Wow, this is a surprise, right? I expected 42 with very high probability, so 43 is quite unusual, right? So that means that the moment I told you 43 was spit out, you're surprised. It means there was information in there. There's a lot of information. And you see, the most unexpected it is, the more unexpected it is, the higher that amount of information will be. So you can see the amount of information as an amount of surprise that you would have if you see that integer. Who is with me? Right? So this is basically the basic building block based on which we are going to define the entropy, is the amount of surprise of seeing a specific integer based on the distribution. Because if I change the distribution, of course, it changes everything, right? If I give you a probability distribution that says it's guaranteed to see 43, and I tell you I saw 43, now it's not a surprise at all. So it does depend on uppercase X. Next, again, I insist because this can give a lot of headaches if you're not careful about that. Uppercase X is the random variable itself. That's my distribution of integers. Small x is a mathematical variable that just stands for any integer. You could replace x with 1, with 42, with whatever you want. But big X you cannot replace with an integer. It's only small x that you can replace. Okay. Now, that's my deterministic distribution, so I didn't put 42 in here, I just put 0. But basically, you see here, the amount of information for 0 is going to be 0 because it's a probability of 1, right? Here's another distribution. That's the one that I mentioned earlier. 1/4, 1/2, 1/4. So now I have a distribution that spits half of the times it's going to say 1, and 1/4 of the time 0, and 1/4 of the time 2. You agree that 1 is going to be less surprising than 0 or 2, right? 0 or 2 are more of a surprise, but 1 happens half of the time. And you see, you just calculate minus of the log of the probability, right? So here, the amount of surprise for 1 is 1. The amount of surprise for 0 or 2 is 2, because that's more surprise for 0 and 2, okay? Now, don't run away. I'm going to introduce another random variable. You know that whenever you have a random variable, you can take a function of the random variable, right? For example, you can have a random variable that is a die roll, right? 1, 2, 3, 4, 5, 6. Then you can have a function that tells you it's even or it's odd, right? Now it's a function that maps 1, 3, and 5 to odd, and 2, 4, and 6 to even, right? That's a function of my random variable. Now, since ix is a function, I can apply it to my random variable, right? So what that means, you can really take the time to understand that. But do you agree, looking at this, that half of the time, you're going to be simply surprised, and half of the time, you're going to be doubly surprised? It doesn't matter if it's 0 or 2, the amount of surprise is the same. So do you agree that half of the time you're simply surprised and half of the time you're doubly surprised? Who agrees with that? So that gives me a distribution, another random variable. Now it's the surprise random variable, ix of x, that tells me half, I'm simply surprised, I'm doubly surprised. And I just took that out of here by basically 1, that's 0.5, and 2, that's the sum of 0.25, 0.25. So that is also a random variable. Who can tell me the expected value of that random variable here? which is 1/2 of the time and 2/2 of the time. What's the expected value? Who knows and just doesn't dare to raise their hand? Just the expected value of that, 1/2 of the time. Who agrees it's 1.5? Right, that's the, okay, awesome. So that's the expected value, 1.5. Well, in fact, that's the entropy. Because the entropy of the Shannon entropy is just exactly that. It's the expected value of this surprise. So you take the expected value of the amount of information with respect to distribution X, but as a random variable. So the entropy of any random variable, you can tell me any source, any source of integers, big X, and I can give you the Shannon entropy of that source, which is just a number. And that number is computed by taking the expected value of the amount of information according to X, which is minus log of the probability. That's it. That's the Shannon entropy. It's not so difficult, but what is complicated is the headache that you get by looking at the formula, right? Just having in mind that here, this subscript means that that's the distribution according to which you compute the amount of information. But what is in here is really just a random variable and then a function of a random variable. That's what happened when I basically took it from here to here. Okay. All right. So that is my entropy. And if I want to compute it, you know how to compute the expected value. It's just the weighted average with the probabilities, right? So I just take the weighted average of my Ix of X for every possible value of small x, and I just compute the weighted average with the probabilities. And if I now replace this Ix with minus log P, I get this very famous formula that maybe you already saw that, the sum of minus P log P. That is the entropy. That's how we get it. That is the expected value of surprise, so to say. It turns out that this gives you the optimal number of bits in average that you can achieve with the experiment that I've shown you. That's the Shannon entropy. So let's compute it on a few examples. Here we have the deterministic source that always gives me 0. So I'm never going to be surprised with that one, right? So the entropy is 0. It's the average of 0 with a probability of 1, right? So it's 0. What that tells us is that if you have this source that always gives 0, Alice doesn't even need to send anything to Bob, because Bob already knows that it's going to be 0 anyway, right? Who agrees? Right? So I don't even need any bits in here. I just don't send anything. Let's look at my other example. The probability distribution, it's also called binomial, by the way, this distribution. It's the Pascal triangle. For those of you who saw it, you know a plus b squared is a squared plus 2ab plus b squared, 1 to 1. That's basically where you get that from. But anyway, I have a probability of 1/4 to get 0, 1/2 to get 1, 1/4 to get 2. And now the amount of surprise, I already computed it. It's simply surprised or doubly surprised. And now, since I'm simply surprised half of the time and doubly surprised half of the time, then I'm 1.5 surprised on average, right? That's my entropy. I have an entropy of 1.5 for here. Here's another example. Uniform distribution over 0, 1, 2, 3. It means that 1/4 of the time it's 0, 1/4 of the time it's 1, 1/4 of the time it's 2, 1/4 of the time it's 3. So always a probability of 1/4. Then what is my amount of surprise? Always 2. I'm always doubly surprised. Whatever number comes out, I'm equally surprised because they all have the same probability. So I'm surprised because I didn't know in advance, but I'm exactly as surprised to see a 0 as I'm surprised to see a 1, basically. So now, what is the average value of this weighted by the probabilities, which I'm completed here? It's just 2, because it's always 2 anyway. So the average of a random variable that always takes the value 2 is going to be 2. Who agrees? Right? Now, do you see that that 2 tells me you can transmit that with 2 bits? An integer between 0 and 3, you can encode it with 2 bits. Who can give me an encoding that does that? A mapping from integers to bits? Just the representation in base 2, right? 0, 0, 0, 1, 1, 0, 1, 1. and this one is optimal. And I know it's optimal because the entropy is 2. So I just need 2 bits, and I will never be able to do better than that. Did you have a question? I think I saw a raised hand. No? Okay. All right, so that's my entropy on a uniform distribution. Who would be able to calculate the entropy for any distribution if I give you the list of integers and probabilities? Yeah, very good. It's always that same, and a number comes out of it. That's my entropy. Here's another one with a geometric distribution. Right? So the geometric distribution is basically powers of 1/2, 1/2, 1/4, 1/8, 1/16. That's called the geometric distribution. In that case, with a factor of 1/2, you can have actually any number other than 1/2. Now you see, with a geometric distribution, the higher the integer, the rarer it is, and thus the more surprised I am, right? So now you see the amount of surprise grows with higher integers, right? Do you see that? Because they are rarer and rarer and rarer. And now it turns out that if you compute the average value, weighted average, weighted with the probabilities, you get 2 again. It also has an entropy of 2. So you can encode that with, on average, 2 bits. But of course, it's not going to be the same encoding as for here, right? You need something smarter, something more involved in here. But on average, the Shannon entropy tells me you will not do any better than on average 2 bits per integer. That's it. Okay, so now that's my entropy. That is basically my theoretical limit. It's what Claude Shannon told me. You cannot do better than that. You will never find any encoding that beats that number right here. So let's see. Let's take some encoding and compute the average length of an encoding. So now I'm no longer looking at the entropy. I'm no longer looking at the surprise. I'm looking at the length. So in that case, I'm looking at the variable byte encoding on 8 bits. So what is the length on 8 bits, variable length of 0, 1, 2? It's always 8, right? And then it's going to be 16 after I filled the 7 bits, right? Who agrees with that? So it's going to be 8, 8, 8, 8, 8, 8, 8, the length, and then at some point 16, and then at some point 32. And then if I compute, of course, it doesn't fit on my slide because it goes to infinity, but if you compute the average of that variable byte encoding size based on that geometric distribution, that gives me 8.00. It's not exactly 8, it goes higher because there's some 16, 32, 64 in there, but they are so small that I'm still very close to 8, right? Now, what do I learn from that? If I use a variable byte encoding for this geometric distribution, I have 8 bits on average per integer. What is optimal? Optimal would be 2. That's the entropy. So that gives me a benchmark. Basically, the optimal is 2, and I have 8. So what the reaction is going to be, say, not so great, right? I could do 2, so 8 is okay-ish, right? I can do it on 8-bit, but it's not optimal. So you see how it's useful to have the entropy. So you can compute what you actually have based on a specific encoding, and then you can compare it with the entropy to see how good you are doing as a benchmark. Here's the gamma encoding. Instead of the variable length, now I'm going to use the gamma encoding on the channel between Alice and Bob. But I still have my geometric distribution right here. I keep the same distribution. Now you see the gamma encoding, you remember that the length is 1 and then 3 and 3 and then 5, 5, 5, 5. By the way, I need to encode 0. So what did I do? I offset the whole thing by 1. Remember? That's my trick to also make sure I can encode 0. So the smallest gamma encoding you have, that's 0. Then you have 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on, right? So, sorry, that was 1, 0, 0, 1, 0, 1. That was 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, and so on and so on. So that's my length for every possible integer. Then I do the average of that, weighted average with the probabilities, and I get 2.266. That's better than 8, right? That was okay-ish. Now, oh, this is good. 2 times 2.266. I'm close to 2, right? So I'm doing well. What about the Unary encoding? Surprise, surprise, the Unary encoding gives you 2. It's optimal with the geometric distribution. That's a fun fact that you can tell your friends, is that it seems like a waste of space, this temperature, this thermometer encoding, but it's optimal for the geometric distribution. It wins over anything else. But there is a difference between the gamma encoding and the thermometer encoding. Is that the thermometer encoding, yes, it's optimal with the geometric distribution, but that's pretty much it. It's not optimal for other distributions. But the gamma encoding, up to a constant factor, it is optimal for any distribution. Any of them is going to be doing very well. Right? So this is why the gamma encoding is actually so nice. So here I took another geometric distribution that just for giving examples, that now is not based on 1/2 but on 3/4, so it's powers of 3/4. Now I find an average length of the geometric distribution of 134, which matches the entropy. The uniform distribution, now you see it's doing less well. If I use the Unary encoding, then I have an entropy of 2.5 instead of 2, right? So you see now the Unary encoding is not so good. And now if I compute the average length of my Unary encoding over a uniform distribution between 0 and 1 billion, then you know it's going to be absolutely terrible, right? Because now I'm going to have a lot of large integers. So you see, this is where it stops. The thermometer encoding is only good at one thing, it's the geometric distribution, period. The rest, it's not optimal. But the gamma encoding, and I'm going to end on that slide, is absolutely fantastic because you have the guarantee that it's basically the entropy up to a factor of 3. It's never going to be more than 3 times the entropy. That is what we call a universal encoding. Doesn't matter what distribution you have, deterministic, geometric, uniform, doesn't matter. The gamma encoding is always within a factor of 3, close to optimal. Okay, who followed? Very good. So I'm going to let you go. Maybe I can just check if you followed with my question right here. I'm pretty sure it's going to output some sort of error message or something. Oh no, it doesn't. Oh, it worked. Okay. Yeah. All right. I'm asking because there was a bit of heavy math today. I didn't get into random variables, but I will show you more mathematically in a couple of weeks, but just wanted to make sure that I didn't lose you too much. Okay. That is good. All right, so thank you very much, everybody. There is a graded quiz this afternoon at 3 p.m. on compression. So you can get, it's your second opportunity to secure the bonus points, 2 out of 3. The third one, I think, is for the vector, sorry? In May, yes, exactly. The third one is going to be later. But if you have 2 out of 3, you get the bonus points. So if you already have the first one and you get this one, you're going to have your quarter points. Thank you, Georges, for moderating. Thank you, everybody, for following this lecture. Hope you enjoyed it. Enjoy the exercise session and see you next week. Yes, right? It's not the vacation yet. So next week for the next course. Thank you very much.